values. But you can see that it works very well at getting this space, and this also scales up to much more complicated problems as well. Okay, does that give a bit more of a flavor of what's going on? Good question.
So in this example, you have a continuous state space and a continuous action space.
In this example, good question, sorry. In this example, there is a continuous state space, which is the position of velocity. The action space, you can do it in different ways, but in this particular example, the action space is either is discrete, so you basically get discrete choices of acceleration. So you either can not accelerate or accelerate, and the amount the accelerate is given. And for some class of interesting problems like this, often there's a class of problems called bang-bang control problems, where actually it's not interesting to consider the space between maximum acceleration and minimum acceleration, because you would always choose to maximize to one of those extremes. And so, yeah, but you can also do this problem with continuous control. But that's a different, that would require, so SARSA would still work. The only question there is how you compute the max. If you've got continuous action space, computing the max is tricky, because you've got to do an optimization just to even find the max. Yeah, question?
In that example, couldn't we use a different representation of the state space and get the function with a much simpler shape?
So the question is, couldn't we use a different representation of state space to get a simpler shaped value function? So that's a great question. So I think the right way to think of this is to say that the state is what's given as part of the description of the MDP, and this is the true shape of the value function. Now, to learn this effectively, you can put in any features you want. So if you think that there's some features, like the features that you provide can indeed transform the shape of the value function to something much simpler. That's one of the reasons to use features. So if you know good features, you can transform this complicated spiral into something flat or something simple to learn. And that's putting knowledge in to simplify the shape of the problem. But this is the value function. This is v pi. You know, v pi looks something like this, and we're just trying to approximate v pi. And so yes, indeed, you can put knowledge in to help figure out this shape of v pi more effectively. Okay. So we talked a little bit about using lambda there. So I just want to throw out this slide, which is like an empirical slide. It's an old one, but I think the lesson has been borne out time and time again since then. So I think it's still useful to see. So forget the accumulating and replacing traces. That's just two slightly different variants in how you use eligibility traces. The story is roughly that across a bunch of different environments, when you use function approximation and something like SARSA, the question is, should you use eligibility traces? And you almost always see some kind of picture like this. This is a cart pole example, this is mountain car. And you almost always have this picture where if you go all the way up to lambda equals 1 and use Monte Carlo returns, you know, performance is really bad. It takes an awful lot of samples to actually get the right result. The variance is too high and you're killed by variance. If you go all the way to TD0, you do better than Monte Carlo. Bootstrapping gains you a lot of efficiency, but there's normally some kind of sweet spot in between, and the shape of that sweet spot depends on the problem and all kinds of things, but typically, you know, having some bootstrapping helps, and lambda can find you something better than TD0. But the main point of this slide is to say bootstrapping typically helps, and so it's worth finding algorithms that are effective when we bootstrap. And so the natural question is, well, is it sound to bootstrap? Like, we know that following Monte Carlo is just like this noisy oracle. We're doing something just like supervised learning, and it must converge. But is that true for TD methods? Do they always converge? And let me put up one situation where they don't. So I'm just going to flash this at you without explaining the example. If you were to do something like this simple MDP, and you were to update instead of using SARSA and actually running on policy, if you were to update this by doing sweeps over the whole state space and doing your updates on all states, you end up with weights blowing up, basically. This is the number of iterations you get, and the weights can blow up. So TD isn't guaranteed to be a stable algorithm. There are situations where you can apply TD where it can blow up, and so it's important to know when it's safe to use TD and when it's not. So this is like a one-slide summary that roughly tells us when it's okay to use TD, when we're guaranteed for TD to converge to something, and when there's a possibility that it might diverge. So the crosses mean there's a possibility of divergence, ticks mean guaranteed convergence to something close to the right answer. And so now we can consider if we're running on policy. So on policy, remember, means we're actually learning from the behavior we're running. So we run our trajectory, and while we're running that trajectory, we're learning about that policy that we're following. So Monte Carlo, great. Okay, it converges for table lookup, for linear, for non-linear. This is all for just policy evaluation so far. We're not talking about control on this slide. But for TD algorithms, if you run on policy and use non-linear function approximation, no guarantees. It can blow up. Like the bootstrapping process can cause divergence in theory. In practice, it tends to work okay. Lots of success stories. But you can certainly construct counterexamples where it blows up. Off policy, even using linear function approximation, it's possible to construct counterexamples like the one we just saw where TD blows up. So off-policy learning can be a little bit problematic. And I just want to mention some more recent methods. So methods such as gradient TD. Also, in the last few months, there's another method called emphatic TD. These are methods which fix the issues that the TD algorithm has when it bootstraps. And we can see that, for example, gradient TD, this is a true gradient descent approach. So instead of just doing this gradient descent and then substitute in the TD target and hope that it's still a gradient, this is something which really follows the gradient of the projected Bellman error. That's a particular objective function. Follows a true gradient. I don't want to get into the details now, but you can look it up. And so it is possible, just with a small correction term, that you basically end up with the same update with one more correction term, and it fixes the problems that we see with TD learning. So you can get convergence, but you have to just be a little more careful with TD. What about when we do control? Control is surprisingly problematic. Like this whole framework of generalized policy iteration, it's very appealing. It gets very efficient algorithms. You've got these very aggressive steps where you take the greedy policy improvement step and you really try and make your policy as good as it can be at every time step. But essentially, we very rarely have guarantees. In fact, almost always we get chattering, which basically means that each time you improve your policy, you might actually make there's no guarantee once you use function approximation that your improvement step is really improving the policy. You might take an epsilon greedy step, but we don't have this guarantee anymore that that's actually making progress at every step, and you can kind of make progress, and then take a step away, and make progress, take a step away, and end up chattering around the optimal policy or the optimal value instead of ever converging to it. So cross here means catastrophic divergence is possible. This means that you chatter, like you're always getting closer but occasionally stepping away, but you never just kind of shoot off to infinity. Right. Okay. Questions before we start running out of time? Good. Yeah. The back there. Yeah, you.
I just want to know when you say convergence is the weights that you mean that they're going to be fixed at a certain.
So what does convergence mean? Convergence means that the parameters of your function approximator converge to some fixed point, and a secondary issue is that fixed point, the right fixed point that we want. And so what this really means is that we converge to a parameter vector that's close to the best parameter vector in the space for our function approximator. Okay. Yep.
You said you can get catastrophic divergence in theory. Are there any of those x's where you would often get catastrophic divergence in practice as a common observation?
So yes, we'll talk about that in just a minute. So using neural networks, if you just naively throw in, say, Q-learning or SASA or something like this and hope that it will work, it very often blows up with a neural network. And that's because, if you use some nonlinear function approximator with like these steep sides, you can really dramatically alter your policy. Your gradient can be very large. You can be kind of shoot off to some new situation. You can end up with these quite complex cycles where you think you're making progress, but now you change your policy and the value function changes in some way that changes the shape of this thing, and you can end up spiraling outwards. it's possible, and yes, it happens. With linear function approximation, I would say, in practice, even if you're running off policy, where we technically have a cross there, mostly it's okay. You sort of have to work a bit harder to break the algorithm. And I would say in practice, you don't necessarily observe divergence. And I'm going to talk about how to address the neural network issues in the next part. Okay, good. So I think we'll have time for talking about some of the batch methods, but I'll leave some to as a reading exercise afterwards. Okay, so let's begin with the motivation. So far we've talked about these gradient descent methods. They're very simple. The updates are really simple. You just move a little bit in the downhill direction, look at your error, move a little bit that way. But they're not sample efficient. You know, we see our experience once, we take an update, we adjust our function approximator in the direction of that experience, and then we throw that experience away and we move on to the next one. That's not data efficient. We haven't made the maximum use of that data to find the best possible fit to our value function and hence the best possible policy. So the idea of batch methods is to try and find, in some sense, the best fitting value function to all of the data that we've seen in our batch. And the batch, in this case, is the agent's experience. That's its training data. It's its life. Like life is one big training set for an agent. And we're trying to basically now fit everything the agent's seen, find the best value function that kind of explains all of the rewards that it's experienced so far. So what does it mean to find the best fit? Well, one definition would be something like a least squares fit. So now, if we want to fit our function approximator to the true value function for our policy, we can, again, define some data set. This is just what we did before. We can say we've got some training set, which is our state and our targets. Like, let's say there's an oracle again. So let's say in state S1, the oracle tells us the value should have been this thing. So this thing is just whatever our target is. We're going to call it V1 pi. That's the oracle consulted for state S1. We consult the oracle for state S2. It gives us another value. That gives us our training set for all of the data that we've experienced. And we remember that whole data set. And now the question is, what's the best fitting value function for this whole data set? Well, we could do something like least squares, which would find the parameter vector that minimizes the sum squared error between the value function and the oracle across our whole data set. So if we consider this whole data set and look at the squared error between what we thought would happen here in the oracle, and the squared error between what we thought would happen here in the oracle, and we want to just minimize the sum of all those squared errors across the whole data set. So that's what the least squares solution does. So it's the sum over all time steps between the oracle value and what we thought would happen, all of those squared errors summed, and we can write that as an expectation over our empirical data set. So this ED means like an empirical distribution expectation over this sum, basically over everything we've seen so far. So we're trying to minimize some kind of mean squared error, the sum squared error over all the data we've seen so far. So that's the least squares solution. And it turns out there's a really easy way to find the least squares solution. And it uses all the methods we've seen so far. And it's just called experience replay. And all it means is that now we make this data set a literal thing. We actually store this data set. So instead of throwing away our data, we cache it. We keep it in some big, we make our training set an explicitly stored object. We have some experience replay memory. And now all we do is at every time step, we're going to sample a state and a value from our experience. So if we were in state S, we're going to sample from this experience. We're going to say, okay, in that state, the oracle said I should do this. We're going to sample that from our experience, and then do one stochastic gradient update towards that target. So this is just like supervised learning again. We've made a data set, and now we're just going to randomly sample from that data set and update in the direction of our random samples. That's standard supervised learning. If you get a data set, you always want to randomize over it and kind of, you don't just want to do the latest things. You randomize to remove correlations. So this is taking our non-IID data, our whole trajectory, and it's randomizing it. It's breaking up into all the little pieces so that we're not presenting things in the order they arrive, which are strongly correlated. We're decorrelating things and presenting them in some random order and just applying stochastic gradient descent again and again and again and again until, where do we get to? We get to the least square solution. Okay, if we just keep doing this, this thing will find the least square solution. It will go over and over this data again, doing gradient descent, and if you optimize for gradient descent, for example, using a linear function approximator, you find the global minimum, which is the least square solution. So if you go over your data, you get more out of your data. That's the idea. It's very simple. You remember everything, you just keep going over your data and squeeze more from that data, rather than just throwing it away after one step and moving on. So let's come back to the motivating example we saw in lecture 1, which is this recent work we did with in Atari. So in the Atari work, we're now in a position basically to understand exactly what we did, actually. I mean, the method's fairly simple, and we can see that now we've basically got all the pieces in place, okay? And it just uses exactly what we've seen so far. So we're going to use basically experience replay and basically Q-learning. So it's off policy, which is a nuance from what we've seen so far. But the idea is really simple, that we just remember all of the transitions that we've seen so far. So remember all of our states, actions, rewards, next states that we see. We remember them in some big replay memory. Every step we take an action according to an epsilon greedy policy with respect to our function approximator. We've got a big function approximator representing Q. We'll see the structure of that neural network in a minute. It's just a big neural network that estimates all the Q values. We use that to pick our actions by acting greedily with respect to our Q values. And then every step, what we do is we sample some mini batches from our data set. So mini batches, not everything, but just a few, like say 16 of these, I think actually 64 we do at a time. We take 64 random samples from our replay memory. So remember, say, a million transitions, sample 64 at random, and follow the gradient with respect to those 64 things. And we optimize the mean squared error between what our Q network is predicting, our action value function, and our targets. And the targets are just something we plug in instead of the oracle. And the oracle, the thing which we plug in is like a Q learning target. So it's just like the SARSA targets, but with a max there. Okay, so we're just looking at the error between what we thought would happen according to our Q learning, according to our Q network. So this is our function approximator. We plug in the error between that and the reward plus the maximization over the actions that we might do next. So this is just like in Q learning. We look at the best thing which I might do at the next step. We want to optimize. We want to say, the value now, we want to update it towards the max over all the things that I might do next. So maximize over all the things I might do at the next step. Use that as a backup so that I now think that the value at this point is as good as the best thing I might have done at the next step. So we make things better and better and better. And then we optimize this using stochastic gradient descent. Now, I said earlier that, that methods like SARSA and TD methods can blow up with neural networks. However, this method is stable with neural networks. And that's one of the contributions of why this worked so well and previous methods just didn't and blew up. And so there are two tricks that make this stable compared to, say, using naive Q-learning, which are these highlighted points here. So the first point we've already seen, which is experience replay. Experience replay stabilizes these neural network methods because it decorrelates the trajectories. So instead of seeing these highly correlated parts of the trajectory, one after the other, we randomize the order in which they arrive, and now you kind of break the correlations and you get much more stable updates. And the second idea is to do, basically, have a second network. So we actually keep two different Q networks, and with two different parameter vectors. And we basically freeze the old network. So we remember our old network, we freeze that for a while, and we use the targets. Basically, we bootstrap towards our frozen targets. We don't bootstrap towards the latest, freshest targets. We bootstrap towards our targets from some steps ago. And that also stabilizes the process. It basically makes it just like supervised learning for the course of one iteration. It's like for a while we move towards the Q values with respect to our old network. And then after we've spent, a few thousand steps updating towards that old network, we switch it around and we make our old network equal to our new network and reiterate that procedure. So we never bootstrap directly towards the thing which we're updating at that moment, because that can be unstable. there's a lot of correlation between your targets and your Q values at that moment. And with neural networks, that again can cause things to spiral out of control. Okay. I'm sure there'll be questions right now, so someone ask. Good.
Sorry, I just don't understand the last part where you said
Yeah.
it's a new network that we're bringing in the same
Okay.
things, but
Good, okay, I realised I was rushing that, so let me just spend a moment to say it more clearly. So we have two parameter vectors. We have any iteration I. Okay, what this is saying is we're going to optimize the loss function for that iteration. And what we're going to do is we're going to update our latest parameters, wi. What we're going to do is we're going to remember some old parameters. So we're going to use some old parameters from, say, 1,000 steps ago. The old parameters are going to be used to generate our target values. So we're going to bootstrap. The oracle now is basically going to, the thing that we substitute for the oracle basically makes use of some old parameters. We don't use our freshest, most recent parameters in our target that we're plugging in place of the oracle. We use some fixed old values. And the reason is that we want to fix this because it gives us a more stable update. We don't want the danger is that with TD learning is that every time you update your Q values, you're also updating your target values. Like if this network and this network are the same, every time you update your parameters a little bit, you're changing the targets to which you're moving them. And with nonlinear function approximation, that can actually spiral out of control. And so all we do is we stabilize that process by freezing this guy to be some old value, and we just update a little bit towards the old frozen values.
so what stage do you go back by? What is the parameter that you choose?
So it's a tune parameter where we basically have one fixed schedule for across all games, where every few thousand steps we move on to another iteration of and adjust these things.
So you don't update them dynamically on the frequencies
You can also update them smoothly, but all the experiments I'll talk about were like a switching. They were just kept frozen. You essentially are then doing supervised learning towards these targets. It's like your targets are frozen for a while. This is also called fitted Q iteration, this idea. You freeze your targets, you update towards those targets, and then you switch in your targets to, your old targets become your new targets. You swap your Q network.
So you wait until you update it to the frozen one before you update.
You don't completely wait. You never get all the way there. This is some enormous neural network, but you just wait some period of time, and then you swap, and you find what works best in practice. I wouldn't claim this is the most aesthetically satisfying idea, but in practice, it stabilizes everything, and the experience replay is really important as well. So just to say, this is the architecture that we use. So it's a big convolutional neural network. If you don't know what a convolutional neural network is, it's just something where you take typically an image, and you have some neural network with shared weights that's applied to the entire image, region by region. And at the end of it, we output Q values for all of our different actions of what the joystick might do everywhere. And we use the same neural network with the same hyperparameters, same step size, same schedule, same rate at which we update things across 50 different Atari games. And these were the results. So this is from the Nature paper, which came out last week. And you see that basically this is ordered by how well we do compared to a human tester that we had in-house, like an expert human games player. All of this point here, everything to this side of it, we're basically doing better than our expert human in-house game player. Everything to the right, we're doing worse. So there are some games which we do horribly at, like Montezuma's Revenge, just turns out to be really hard. And a lot of games where we do, way better than human, like in video pinball, or things which are very twitchy. So the algorithm is robust. This indicates the robustness. How well do those two ideas help to stabilize it? So we see experience replay makes a huge difference to the stability of the algorithm. This is the performance on, say, 5 different games, with and without replay, and with and without this kind of idea of switching the Q networks. And this shows that both of those ideas help, and the combination of the two of them makes it the most stable and effective. Okay, so all of this was just an example of one simple idea, which is stochastic gradient descent with experience replay as a way to squeeze more out of the data that you've seen so far. I just wanted to make that practical. But are there methods where we can jump directly to the least square solution? And the answer is yes for the special case of linear function approximation. So in the remaining few minutes, I just want to give you a flavor of what that looks like. Okay? So it's... so why should we care about this? You know, we have this method of experience replay. It's very effective. It's incremental. It's any time. You kind of do as much replay as you want, and you get closer and closer to the solution. But sometimes it can take many iterations to really get to that least squares solution. And if we really are using linear function approximation, there's at least a, you know, with more computation per iteration, like you can do a little bit more in one step and jump all the way to the correct least squares solution, closed form. Okay. And so it's like you can do your policy evaluation step in one jump. And so it looks a bit like this. So I'm just going to do it with one case, like using the oracle again, and then you'll kind of see how to plug in all of those different estimators, whether it's the... So we're going to consider some oracle, again, v pi t. This is at time step t. What's the oracle say the value was? And then you can plug in, again, your Monte Carlo estimate or your TD target or your lambda return. You can plug in anything you want there. But the idea is really simple. The idea is just to say, you know, at the minimum, at the least squares solution, what does it mean to be at the least squares solution? Well, it means that we're not going to change our weights anymore. Like that we wouldn't choose to update our weights in any direction anymore because we've reached the minimum. Like if we were to keep going over our data again and again and again, we wouldn't make any more changes because we're happy we've reached the best solution we can get to. Okay? So another way to say that is that if we take the expectation over our data set, like this sum squared error, of our updates that we would make, we would want the sum squared error of all of our updates over a whole data set to be 0. We don't want there to be any pressure to change this thing. If this was not 0, you know, if this was positive, you know, we would still want to be moving. We'd still choose to change our weights. So that would mean we hadn't reached the least squares solution yet. And then the rest of this is just expanding that, okay? So this is unwrapping the sum squared update. So this is, sorry, I said the sum squared error. What I meant was the expected update. Expected update. And the update depends on the sum squared. So if we unwrap the expected update and look at the update that we're making over a whole data set, like how are we adjusting the weights over a whole data set, we're basically saying for each sample, we've got, this is our update. We've got, like for each of these, for each time step, we're moving a little bit in the direction of the step size times the error between our linear function approximator here and the oracle multiplied by the feature vector. That was our update. That was the linear, you can go back up and check if you don't believe me. Step size times error times the credit, the gradient vector, which is just the features in the linear function approximation case. And we want the sum of all of these things to be 0. We want the average gradient, you know, the average gradient of our objective function to be 0. And so we just collect these terms now. We've got one term here, and another term with this x times this x here. That's just collecting terms. And then we see that only one of these depends on w. And so we've just got this big matrix here, which is the outer product of your features. And so we can invert that to get the solution for w. So with a little bit of linear algebra, you can start off with this idea that you want your update across your whole data set to be 0. With a little bit of linear algebra, you can see that you can bang, just by inverting a matrix, you can get the right solution. Now, inverting a matrix, we've been avoiding doing this because it's expensive. But the cost of this doesn't depend anymore on the number of states. Like this depends only on the size of our feature vector. So if we've got a small number of features, this is reasonable. So inverting it takes order n cubed. And better still, you can use something called the Sherman-Morrison-Woodbury trick for incremental matrix inverse. And you can do this in n squared time. So it is possible to get a more efficient update that's got quadratic cost in the number of features you have. So the point is you can go bam, straight to the solution of your least squares. In other words, squeeze the maximum juice out of your data with your linear function approximator, find the best weights. And sometimes this is better than experience replay. Like if you've got a small number of features, but some complicated history of a lot of experience, this might be cheaper to do. If you've got a lot of features, it might actually be better to do experience replay. You might get closer to the solution by doing some amount of experience replay. You know, maybe I had a lot of experiments where, you know, just after 5 or 6 repeats over your experience again, you already get close to you extract most of the juice out of the data you've seen. And so you can really get an awful lot with experience replay. But this is also appealing because, bam, in one go you get right there. That's, you know, specific to linear function approximation. Okay, so as I said, we can plug in Monte Carlo returns, we can plug in TD targets, we can plug in the lambda return, and you end up exactly the same updates. This is just plugging in the same idea of making the update equal to 0 overall, and then solving for that update. And you end up with algorithms called least squares Monte Carlo, least squares temporal difference learning, and LSTD lambda. And so, how do these fare in terms of convergence? Well, they actually have better convergence properties than the incremental ones. So, in particular, so they can't be applied with nonlinear function approximators, but they do converge both on and off policy to the right answer. So they have less issues compared to TD with this off policy case. They, bam, get you the right answer. Doesn't matter if you're learning off policy. And then finally, I just want to say that how do you actually use this in practice? Well, you apply an algorithm called LSPI, least squares policy iteration. And again, we're back to our familiar approach to doing control. Like if you really want to solve for control, so far we've just talked about how to do policy evaluation. We solve for the least squares fit to our current policy. But what if you want to use that to do control? Well, now we're just going to plug this same idea in again. We're going to replace our policy evaluation step by a least squares approach to learning the action value function. So we want to find a least squares fit to Q. If we replace our V with Q, and now we can basically come back to this approach here. We're going to start off with some weights for our linear combination of features, act greedily with respect to our Q, and then do our least squares fit to all of the data we've seen so far, generate a new Q value, act greedily, do a least squares fit to all of the data we've seen so far, and iterate and so forth. If you do this in the right way, it converges to the optimal value function and the optimal policy. So there's a few more details in the slides which roughly just outline a little more detail on this algorithm. It's called least squares policy iteration. And show that this also has, you still have some issues. I mean, when you move to control, this still can chatter. So it's not like this solves all the convergence issues. And then I just want to show one final example, which is like this random walk type example with some more complicated dynamics. So this is a problem with like 50 states, and they're just, so 50 states, and it's like a replica of this diagram, with these different dynamics over 50 states. And now we just say there's 2 good states that we want to get to. So there's a reward of +1 if you reach state 10 and state 41, otherwise no reward. And we're going to use function approximation with some kind of radial basis functions, some Gaussian spaced around, kind of generalizing across some of these states. So we're kind of, we don't have a separate value for each of these states, we're going to generalize across them. And now we're going to apply LSPI to this chain walk. And you see in just a small number of iterations, so this is only 7 iterations, it's finding the optimal value function and hence the optimal policy. So here you see this is basically showing the state space along this axis. And so you see here, here's the good state, state 10, here's the good state, state 41 or whatever it was. And it very quickly picks out the shape of this. So the blue and the red represent the 2 different actions of going left or going right. And so the other parameter of dashed versus solid is whether it's the true value function or the approximate value function. And you see that it very quickly figures out the perfect shape to this thing. And it's approximate, it's not like a sharp peak because the value spreads out a bit, and also because we're using function approximation. It very quickly gets the structure, like, you know, evaluates its starting policy, ends up with a shape like this, acts greedily with respect to it, ends up evaluating that new policy, gets a shape that looks something like this, improves its policy with respect to that, ends up with some new value function and so forth, and after just a small number of iterations it arrives at the right answer.